All right, everyone, welcome to Chapter 15, Section 5, Vodcast. All right, so make sure you have your guided notes, and it might be helpful to have your textbook this time open. I'm starting here on page 641, and I've got a calculator too. So all of that stuff might be kind of helpful before we begin. All right, the whole purpose about Section 5 in your textbook is being able to calculate that darn equilibrium constant. So we are going to start off really easy. We're going to start off with calculating the equilibrium constant when you know the concentrations of all of the reactants and or products at equilibrium. So let's take the example here of the formation of ammonia. Okay, this is the Haber process. So what I've done here is I've given you the partial pressure of each of the gases, and I've shown you the equilibrium expression. So from here, you need to realize that sometimes the equilibrium constant can be used with partial pressures or obviously with molarity. And as long as you have the concentration of all of the reactants and products at equilibrium, it's pretty easy to do the equilibrium constant. So at this point, you need to refer back to how to get your equilibrium expression. So remember, your coefficients become the power. Just make sure you put the products on the top and the reactants on the bottom. Just like that. And you'll notice that I used K sub P. I'm not using K sub C because K sub C is for concentrations of solutions. All right, now let's fill in the values that we were given. All right, now finally, let's grab that calculator and let's get an answer. And you'll notice that the answer is pretty small. In fact, it's a -5 on that power. So you can kind of see by looking at this that technically the denominator value is larger than the numerator, which means that the reactants have a higher concentration than the products. In this particular example, it seems like your reactants are being favored. So now we move on to a little bit of a tougher way of calculating that equilibrium constant. So some problems, what they'll do is they will give you just your initial concentrations of like maybe some of your reactants or maybe some of your products, and then they'll only give you one of the equilibrium values of either the reactants or the products. Welcome to the ICE tables. Insert Vanilla Ice music right here. Okay, but anyway, the I in ICE stands for the initial. This means initial concentration. The C stands for change. Change meaning like, the reactants are going down, so you'll typically subtract from the reactants, and the products are being made, so the products are usually a positive value. So you consume reactants and you make products. And then E stands for equilibrium. What is the concentration at equilibrium? ICE tables, ladies and gentlemen, are extremely important. So here's an example where information is provided in a problem. They gave you the initial molarity of hydrogen and iodide, but at equilibrium, the only one that they give you is the concentration of your hydrogen iodide. That's it. So a couple assumptions that you can typically probably make is that none of the product has, at the initial stage, none of the product has been made yet. There's no initial concentration of your HI. You see how that's your product. Now, I want you to notice that the change in the middle, okay, has not been completely filled in. But you do realize that when you started the reaction, none of the product existed. Therefore, there had to have been a positive change of 1.87 times 10 to the -3 molar. You see, a lot of people, when they first learn stoichiometry, you guys remember that, stoichiometry? Like, hey, I've got 15 grams of this and 4 grams of that. How much product can I make? A lot of people learn stoichiometry the very first time using ICE tables. So you just look at mole ratios from the balanced equation. So at this point, you look back at the balanced reaction, and you'll notice that there is a coefficient of 2 on this HI. So this change that you see right here represents actually 2 times what the change would have been for these guys. See how they have a coefficient of 1 in front of them? So what I need to do mathematically is I need to take the 1.87 times 10 to the negative 3 and half it, right? And remember, these are reactants, and so they're going to be consumed. So I want to make sure that whatever number I place over here for these reactants H2 and I want to make sure that I am decreasing the overall value because those are the reactants being consumed. All right, calculator time. So just some simple math here. I got 9.35 times 10 to the negative 4. Now I'm going to take the initial, you see how we have initial concentrations for both of the hydrogen and iodide, and I'm going to subtract the change. This is half what that was, okay? So I'm just going to calculate this out, and I'm going to get my equilibrium concentrations for the reactants and the products. Now that I have the concentrations of both the reactants and the products at equilibrium, all I have to do now is to stick it into K sub C. So just remember, look back at your balanced reaction, and you always put the products on the top, and then look at their coefficients. So HI is going to have to be squared, and then your H2 goes on the bottom, and your I2 goes on the bottom. All right, now plug in all the values that you got. Calculator time. All right, I got an answer of 51. And this is just like sample exercise 15.9 on page 643. Now I want you to notice that the value is larger than 1. So you really kind of have to think about what that means. The numerator would be greater than the denominator. And the numerator are your products. So in this particular equilibrium, it looks like the products were favored. Okay, now it's time to move a little bit further on into chapter 15. We're going to hit section 6, or what I affectionately call getting nutty with K equilibrium and ice tables. So now that you got the gist of how K equilibrium works and how to set up ice tables, like the very, very basics, now it's time to get a little cray-cray. So ice tables and K equilibrium, I can basically, it's like solving a puzzle. I can pull certain pieces out and put certain pieces in so that you have to either figure things out through stoichiometry or some really crazy math. So one of the ones that I wanted to show you was actually the sample exercise that you guys see on page 646. So if you could flip there. The first one that I want to show you is sample exercise 15.11. Let's check this one out. So now they start throwing you some curveballs. They say, all right, we've got the pressure at equilibrium for the nitrogen, for the hydrogen. We just don't know the partial pressure of the NH3 at equilibrium, but hey, we have the equilibrium constant value. Okay, so you just need to think critically. You need to think like you're solving a puzzle. What's missing and how do I solve for that? You know what your equilibrium expression should look like. So you start plugging stuff in. You've got an unknown value for the ammonia, NH3, but we do have this value for KHP. So this expression is equal to 1.45 times 10 to the negative 5. All right, start plugging and chugging and solve for your X. All right, so this value is the partial pressure of ammonia at equilibrium. The next sample problem, 15.12, really gets things cooking here. So part of the problem is that students need to be able to read what the question is providing for you. So what we got here is a 1 liter container filled with 1 mole of H2 and 2 moles of I2. Right? It says the value of the equilibrium constant for that at 448 degrees Celsius is 50.5. Now it wants to know what the equilibrium concentrations of H2, I2, and HI are in moles per liter. Now there's some very important information that was provided that you need to make sure you heard. You have a 1 liter flask. That's important. In that 1 liter flask, you put in 1 mole of H2. So technically your initial concentration of H2 is going to be 1.000 mole. And then you heard that they stuck it into a 1 liter container. Technically it's 1.000 liters. So you see what I've done here is I've done concentration molarity. Okay. Oops, sorry, I put that in the wrong spot, I think. Oh, wait, no, I got that in the right spot. Sorry, my bad. Okay, and let's see. Now they've got 2.000 mole, 2.000 mole of I in a 1.000 liter container. Okay. Now, what did I say about the initial concentration of your products? So this is an equilibrium, right? The initial concentration of your products, remember, if it's not given in the problem, it's probably a 0 because we haven't started the reaction yet. Okay, so it's okay to put a 0 in there. All right, and now you're probably saying, okay, where do I even begin? They gave me a K sub C, so remember K sub C is concentration, value of 50.5. But they didn't give me anything else. What am I supposed to do? At this point, you are going to rely on your stoichiometry skills. You know, look at the balanced reaction, you know that you're going to consume a specific amount of hydrogen and that whatever the amount of hydrogen that you use, it'll be the same amount for iodine because it's a 1-to-1 mole ratio. So what you can say is you know that hydrogen is going to lose a very specific amount. We'll call it X. I will also use whatever that amount is. It's going to be the same because it's a 1-to-1 ratio. But for hydrogen, for hydrogen iodide, your product, you see how there's a coefficient of 2? Well, if we consumed X, we should make 2X. Remember, positive. We should increase by double whatever those other amounts are. Okay, so this looks a little complicated now, huh? But let's get our equilibrium. So this is technically 1.000 molar minus X. This guy will be 2.000 molar minus X. And then this guy is just 2X. You're probably thinking that you've got nothing to go on here. But with some algebra, we can actually figure out this stuff. So here's your K sub C expression. Let's plug into that K sub C, the 15.5. Let's put our products, which is 2X. This is going to be on the numerator. Make sure you square it, because there was a coefficient of 2. Let's get our hydrogen in there, 1.000 minus X. Right, and let's get our iodine, which is 2.000 minus X. All right, so you're looking at this and you're like, oh my gosh, that's some crazy math. Well, that's why we have a fairly stiff math prerequisite for this class, okay? So you can solve for that X, you can. It's going to take some time. You're going to have to kind of rearrange this sucker. So let's see what kind of mad skills you have. Go ahead and pause this video and see how much you can simplify. Okay, so what I've done so far is I've kind of foiled out the numbers on the bottom. So I took this part right here and I just kind of foiled it. So now I've got my denominator. On the denominator, I combined like terms, and now I'm going to move it over to the other side. And of course, I set that equal to 0. At this point, those of you who have a graphing calculator with an algebraic quadratic equation solver, you're set. Like, you can have your calculator do this for you. For the rest of you, though, if you don't have a quadratic solver, you're going to have to do it the old-fashioned way. Do you guys remember how to do it? All right, there's your quadratic solver. If you have to do it the old-fashioned way, just make sure that you realize that there are 2 different possible answers. But only one of them is really going to make sense. So typically, when you do these quadratic solvers, you're going to have a positive value and possibly a negative value. Now I want you to look back at your ICE table. Look at X. Would it make sense if your X was a negative value? I don't think so. We want to make sure that X has a positive value because we want to actually consume it on the reactants and make it on the products. So just keep that in mind. This time when you solve for X, you're going to get 2 possible answers. X can either be 2.323 or it could be 0.935. So looking at these 2 values, come up here and look at your ICE table. Okay? Do you really want your x value to be larger than 2? Can we go into negative concentration here? No, that's not possible. So the better solution for x is this guy. Well, now that you've got your ICE table set up and you finally solve for x, you're going to have to actually go back to your ICE table and plug that value in and start solving for your equilibrium constants. And for your equilibrium, oh wait, we already have our equilibrium constant, my bad. You need to solve for your equilibrium values. Okay, so take the 0.935 and start plugging it in for your x values. And voila, you've got your equilibrium concentrations. Now I've got a sample exercise of my own making. So here we have dinitrogen tetraoxide and nitrogen dioxide. And let's just pretend that we take a container and we pump the container with 3 atmospheres of the dinitrogen tetraoxide and 2 atmospheres of the nitrogen dioxide. And then I tell you that we're going to reach an equilibrium, and the equilibrium is established at 25 degrees Celsius. And we take note at that equilibrium that the nitrogen dioxide's pressure has dropped by 0.952 atmospheres. I want you guys to solve for K sub P. All right, let's do it. So you notice that I filled in the ICE table here for my nitrogen dioxide. So the pressure of the nitrogen dioxide dropped by 0.952 atmospheres. But what you need to see here is if one of them, if in this case, the nitrogen dioxide dropped, that means that the other one should have the opposite. It should increase. But you also notice, you see the coefficient here of 2? If we're going this way, it'll be the opposite sign, right? But it'll also be half that because there's no coefficient of 1 on that. All right, so you got to be really careful. It gets kind of sneaky sometimes, these equilibriums. Let's finish the ICE table and solve for K sub P. So just remember, products over the reactants. The product had a coefficient of 2, so make sure you square it. Now let's solve. I get 0.3160. Let's try another example. So in this particular example, they gave you the initial concentrations of your reactants, and then they gave you your equilibrium constant. What the question is asking you for are the equilibrium concentrations. Okay, so this is the one where we don't have any equilibrium value for any of those reactants or products, but we can kind of anticipate what the trend should be in change. Lucky for you this time, everything was a 1-to-1 ratio. So remember, if it's not given, assume that the products have an initial concentration of 0, because we haven't made any products yet. So you'll notice in the balanced reaction, and this is balanced, that everything is a 1-to-1. So if I consume X of this reactant right here, if I consume an X of that, this will also be an X because it's 1-to-1. And you see how this also does not have a coefficient? So we're going to make X. We just need to solve for X. This is kind of nice. I gave you an easy problem. So let's get the equilibrium amounts. This guy is going to be 0.335 minus X. This will be 0.526 minus X. And this will just be X. And look, I gave you your K sub C. So just remember, it's always products over reactants. So we can kind of set it up like this. C2H6 will be on the top, and your C2H4 and your H2 will be on the bottom. And remember, it has to equal 0.99. So we can start putting in some values. All right, let's start reducing. I'm going to get that stuff on the bottom kind of reduced and push it over to one side. 1.77 or 0.0992. So let's look back at the ICE table and see which one makes more sense. So coming back to my equilibrium calculations here, would it make sense if X was 1.77